Okay, let's start the class. About tipping. Anyone here still having a problem with tipping? Okay, as I told you yesterday, as I told you guys yesterday, we have three types of tipping condition. Okay, three types of tipping condition. The first one is condition where it just stays stationary. So it's the same as what you have done before in the right friction. Okay, that's the first one. Okay, it stays stationary. The second one, okay, impending motion. Okay, the second one, impending motion. The same as in the right friction. The third one, okay, the third one is it's moving, translation. That's the third one. The fourth one, okay, instead of moving translationally, it tips over. Okay, so we only have 4 cases in the tipping condition, is something like this. And how to check which one is happening? Okay, what you're supposed to do is just to check the fourth one, whether it's happening or not. That's the first thing to do. How to check that is by checking the critical condition of tipping. Okay, am I there? Am I doing this? Oh, yeah. Oh, you are TV. Why I'm looking at you? Sorry, I have a question. Am I there? About how to check the critical condition of tipping. Yesterday I talked about it. If the case is like this, okay, which one is it that is the critical condition? Yep, between those two pictures. Yep, this one is the critical condition. So the critical condition is when the normal force and friction force, okay, the condition where normal force and friction force happening on the edge. That's the critical condition. That's the thing that you need to check if you want to ensure whether it's tip over or not. That's the first one. Okay. Then after that, based on your based on that particular case, okay, if so actually if this one is happening, this one is impending tipping, right? But when we want to check whether it tips over or not, the things that we normally calculate is this one, X. Okay? So when we have a case like this, what we have to do is when we have to check whether it tips over or not. Okay? How can we check it? Yeah, how can we check it? We just need to use sigma moment at this particular location. Sigma moment at this particular location. Okay? We have X value there. We know P and W. Okay? We know P and W. Then, based on P and W, yeah, with X as well, we will know the value of X. If the value of X exceeds P, this particular P means the location of the normal and friction force is outside of the edge. What does it mean? It tips over. Okay, but if it's still in this area, means it's not tipping over yet. That's the thing that you have to do at the beginning. Just check the X value. Check where the normal force and friction force will be happening. If it's outside of the edge, okay, beyond the edge means it will tip over. Because it's not possible, right? The maximum that is still possible is like this. At the edge. If it's happening, what does it mean? And what does it mean? If it's happening, this kind of thing is happening, what does it mean? No. Impending tipping. About to tip over. Okay, this is the condition of impending tipping. So later, if somebody asks you, what is the maximum pushing force for certain age like that? Or what is the maximum age for certain P like that? Okay, to ensure that it's not tip over, this is the things that you have to check. That's the case of impending pitch. Okay? So when we talk about tip over, yeah, if all the value P and H are known, in order to check whether it tip over or not, check the X, find the X. Okay? But if the question is, what is the maximum P or what is the maximum H, like that? Okay, what you're supposed to do is to check the condition of impending pitch. Okay, because impending pitch will give you the maximum P for certain H or the maximum H for certain P, right? Okay, any question about pitch? Before I go for the next discussion on the wedges. Yep.
The X cannot exceed the half length, right?
Yep. It cannot exceed in order for it, in order to ensure that tipping is not happening.
I mean, exceed to the left.
You mean this one?
So the minimum value of X is on the middle of the length, right?
In this case, yes. Yeah, in this case, yes. But sometimes the force is from the right to left. Right? So as long as the F and the N is still in this area, it's supposed to be tipping is not happening. Okay. Any question about it? No? In that case, I will continue the discussion on the okay. Okay, the next one I want to discuss about wedge. Okay. Okay, I want to discuss about wedge. Okay, as I told you yesterday, wedge here is not the shoes that normally girls use, but in Bangsa we call it as pasak. Okay, the things that you normally put under the door in order to ensure that the door is not moving. We call that as a wedge. Okay, why we talk about wedge is because the way it works, it depends only on friction. Okay, it depends on friction. The coefficient of friction in this surface, coefficient of friction in this surface, right? And this particular angle, that's the things that will affect how wedge works, right? Okay, and when we talk about wedge, okay, we will talk about when we put it in, what is the force needed to put the wedge in? Okay, and then we can talk as well about the amount of force needed to pull the wedge out. Okay, those are the things that we normally talk about. And the third one we will talk about as well about condition where the wedge is self-locking. The meaning of self-locking, okay? If you see a wedge on the door like that, normally when you put it in, it will stay there. But sometimes if the angle is too big, okay, if the angle is too big, the angle of the wedge is too big, okay, without any pushing force, the wedge will come out by itself. You get it? Something like this. If the angle of the wedge is too big, right? The mass beyond that will push the wedge down, right? So the wedge will move out by itself without us doing anything. Okay, so that's why when we talk about wedge, the things that we will talk about is the force we need to push it in, the force we need to push it out, to pull it out, and the last one is to ensure the self-locking. Okay, those are the things that we will talk about wedge. Yeah. Anyone here have used wedge before? No? Yeah, use it or what? How about you? Okay. Yeah, normally that's one of the things that we one of the application of wedge. Okay. Now, if we want to talk about, if this is the case, right, we push the wedge in, okay, what is the amount of force needed to push the wedge in? Okay, the least amount of force to push the wedge in. If I ask you about it, what we supposed to do? Anyone have any idea? That's your wedge jacket, right? Because you are so proud of your wedge. Please answer the question. Yes, I saw some. Is it double-sided or just one-sided? Why you call it as Gelora? Gelora Spartan? Oh. Why you put Gelora? This is your wedge jacket, right? Your wedge only in our faculty or the other faculty? Only our faculty. What does it? Huh? Is there any special meaning behind Gelora? Yes, but anyone else? Bibi, you seem sleepy, right? Okay. Would you mind to explain what is this? What is this? You don't know. So who made it? Huh? Then? So why everyone looking at it?
I was because you were on the bike, but I didn't design it.
Oh, you are for I see everyone looking at it. You are the coordinator. Who decided? Fauzan. Oh, Fauzan. You. What does it mean, Fauzan?
I don't know.
Yeah. So what is stand for? Sembilan, loyal, kemana? Why? You know what?
I'm part of my identity.
Wow. But you're intelligent.
Oh my God, everyone.
Oh, you don't know about it. Okay, anyway, because you're using the jacket and you are so proud of your jacket, you have to be able to solve it. Okay, good. I want to need the minimum pushing force in order to push the wedge in. How can I do that? How can I calculate it? What I supposed to do? What's the steps that I supposed to do? Right? Supposed to do. You start. I believe it's not your name. Oh, you like stick that much. Okay, so sorry about that. I always try to find subjects inside of our class. Like later, when we use our time jacket or our course, you can tell what's the name. I'm jacket or I'm materialis. MTM jacket. Normally those who are using jacket is the one that I will point out. No. I know that you only use jacket, right? So what we supposed to do? Now you're missing a step. Always free body diagram. Okay, start with free body diagram. Which free body diagram that we have to talk about? The wedge part. Okay, let's see the wedge. And what forces that we have here? B. Okay. What else? Ground, normal force. Okay. What else? Normal force, yeah. What else?
Weight.
The mass, but this one is normal force from the ground. This one will be a normal force as well, but from the weight, right? What else? Friction from the floor. The direction is supposed to be which direction? Friction. When we talk about friction, the direction of the friction force is supposed to be in which direction? Opposite of what? Not the force. Opposite of the impending motion. The direction of the motion that it can be if the force is exceeding the friction force, right? So, if we give a pushing force to the left, okay, the motion most likely will be to the left, right? So, in this case, the friction force will be to the right. Friction from the ground. What else? From the mass as well. It will be friction force, right? But the direction is like this. Why is like this? Because friction force is always perpendicular to the normal. Okay? Normal force is always perpendicular to the contact surface, like that. Yeah? Normal force is always perpendicular to the normal contact surface. Friction force parallel to the contact surface. And the direction is supposed to be the opposite of the impending motion. The motion that will happen if the force exceeds the friction force. So this is it. Although I made a mistake here, it's slightly slanted, right? I'm sorry for it because it's been a while since the last time I used whiteboard. But I want to make it straight up. Okay. So this is the free body diagram. Okay, if we know the value of mu s between the ground and the wedge, this one is mu s ground equal to 0.5, for example. And if we know as well the mu s between the wedge and the mass, the weight is, for example, in this case 0.55. It's different like that. Okay. when we talk about the least pushing force that we need in order to ensure that the wedge is going in, what we're supposed to use for the friction force here and here. You get my idea? No? Really? You get it? No, okay. So basically I'm asking, okay, the least amount of free force to push it in. Okay? If I ask about the least amount of force, okay, in order to ensure that it's moving, right? At least it's supposed to handle the maximum friction force due to the static friction force here and here, right? Correct, correct. If I give more than that, of course it will move much faster, right? But the minimum is just slightly more than the maximum static force here and here. Correct, correct. And that's the normal thing, and that's the normal, that's the things that is normally asked. The least amount of force to push it in. Okay? So in this case, we can replace this with what? We can replace this with what? Still in shot. Okay, you forgot about friction force is normal force times the mu. Okay? You don't have to take a look at your notes. Okay? So it's energy times mu s t like that. And this one NW multiplied by mu s double. Right? Okay, now if we take a look at this, can we solve it or not? Pushing force P, we have energy, mu s g we have it, mu s w we have it, and w we don't have it yet, and g we don't have it. Can we solve it? Yep, Triano. Can you solve it? But in this case, it's because there is no distance there. Okay? We only have two equations, unfortunately. Instead of three, okay, we only have three. Sorry, we only have two equations in this case. Yeah. What we have, right, is only sigma fx equal to 0, sigma fy equal to 0. Okay, when we talk about wedge, because normally we don't have the dimension, only the angle that we have here. The angle alpha here. Okay, this is normally the equation that we have. Only those two. And unfortunately for us in this case, we have three unknowns, right? P is unknown, and G is unknown, and W is unknown. So we have three unknowns. Only two equations. Can we solve it? No, we can't. So what we're supposed to do, like what I taught teach you guys in order to solve for frame is, if we try to solve for one multi-force member and the number of equations is not enough, what we're supposed to do? You can take a look at the whole, yes, that's one of the way. Or you can try to find another free variable, right? That's the way to solve the problem in the frame, right? The way to solve here is the same. The way to solve this particular wedge problem is just the same. Whenever you don't have enough equation to solve your others, try to take a look at other possibility. Try to take a look at other free body diagram. You can try to take a look at the whole thing, or you can try to take a look, you can try to take a look at the other free body diagram. Do we have other free body diagram here? Which one? The mass, correct. We have the mesh. Okay? If we talk about the mesh here, what forces we have at the mesh? Remember, right? Normal force there, friction force there, NW and FW is supposed to be action and reaction, right? Between the mass and the wedge, right? So we supposed to use this as well, in this particular free body diagram. Okay, Elsa, please point out one of your friends to solve this, to help you. The one that you think is very loyal to your pet second. Beside you, there's no one here using your pet second. No. It is more interesting to ask directly to the person. Alright. Okay, alright. Actually, you are which school? Okay. Yesterday I asked you. You haven't asked me yet. Okay, good. So, what forces that we have there at the base? You have a problem there. Okay, why didn't you tell me already? The weight, correct? The weight is supposed to be there at the center of gravity. What else? The what? External force from the side. We will talk about it later, but try to put this here. Normal force supposed to be there. And W is supposed to be there. And what is the direction? Remember action and reaction, the third Newton law. So if it's going to the bottom, right? This one is supposed to be going top left, right? Yeah, action and reaction. So it's supposed to be going to top left. At the same angle, okay? This one is NW. What else do we have? What about friction force? It's action and reaction as well. Okay? If it's this one, okay, going to the top right, this one is supposed to be going to the bottom left. Yes, correct. Yeah. What's that? FW, so FW equals to NW multiplied by mu S W. Okay? Now, if all the reaction here is going to the left, the reaction from the ground here and here, the resultant is supposed to be going to the right? Okay, so we just put it here. One is supposed to be now to represent all from the left and the right. Okay, so this is the resultant of the reaction at this roller and at this roller. The total one. We don't have to find out the individual reaction there. What we need just the total one. So this one is the total one. Total reaction. Okay. Now still algebraic free. If we know the weight here, okay, and we know the MSW here, Will it possible for us to get the NW and R? How many unknowns that we have in the left free body diagram? Try to list it out. The unknowns, the one that you don't know the value yet. Which one and which one? R, we don't know, yes. And W, right? We don't know it. So we have 1, 2, right? 2 unknowns. 2 unknowns, and how many questions do we have here? Only 2, because we only have sigma fx equal to 0 and sigma fy equal to 0. So if we call this as the first free body diagram, and this one is the second free body diagram. So this one sigma fx1, sigma fy1. This one is sigma fx2, sigma fy2. Okay? Try to take a look at the first free body diagram. We have 2 equations, we have 2 unknowns. Can we solve it? Yep, you can. Okay, just using sigma fx equal to 0, sigma fx1 equal to 0, sigma fx2 equal to 0. Sorry, sigma fx1 equal to 0, sigma fy1 equal to 0. We will be able to solve for R and NW. Okay, because all the friction, all the coefficient of friction, we know it already. After you solve that, you get the value of NW. You can bring it here. Now it's left with only 2 unknowns, right? P and G, which we can solve. So that's the way to solve it in this case. When we push it in further. Okay? Any question here? Raja, you have any question? You understand? Okay? So it's roughly there. This is what we normally have. The value that we have normally have W, mu S for the ground, mu S for the weight. The ground and the wedge. This is the weight and wedge. Okay? Those are the values that we normally have. Okay? And the results that we need is this one, I think. The least amount of force needed to push it in. So in order to ensure that the wedge is homing, okay? Because the one that we calculate here is the condition of impending motion, right? Impending motion, because we use mu s t and mu s n. Okay? The amount of force here that we want is the amount of force of impending motion. So in order to ensure that it's going in, it is supposed to be more than. So the force supposed to be more than the force that we calculate here. Okay? Because the one that we calculate there is impending motion, right? Any question? That's the free body diagram when we push the wedge in.
Why do you make mass not use?
That's right.
If you measure the weight mass not use.
If the wedge has a mass that is not negligible, so you cannot neglect that, then you have to put the wedge of the wedge. But most of the time, we can neglect the mass of the wedge because it's way less than the mass of this one. Normally it's way less, so most of the time we can ignore it. But if it's stated in the problem, then we have to put the weight of the wedge here. Okay? But normally, because it's very small in comparison to the mass of the weight here, this one normally is neglected, the mass of the weight. Okay? Any question? For those who are at home, can you follow me? So this is the resultant force. Okay. You can see that R1 and R2. R1 is the resultant between Fg and Mg. R2 is the resultant between NW and FW. That's why the direction is like this. Okay? But anyway, you can just put it individually like this if you are confused about this. Okay? You can put it individually like this. Okay? If you put it together, P here is actually related to your mu actually. Okay? Because as you can see here, the x component is Ng multiplied by mu Sg. The y component is Ng. Right? So if you total both together, okay, if you total both together, this one is Ng, this one is Fg, which is equal to Ng multiplied by mu Sg. Okay, if you want to sum both together, this is the resultant. And the resultant actually that will have an angle. P. Angle P. And the angle P there will be directly related to mu SW. Because if you get that, okay, the tangent P will be equal to what? If this one is P, tangent P there is supposed to be what? Divided by what? Fg divided by Ng, right? Fg divided by Np, where Fg is equal to Ng mu St divided by Ng. So tangent P here will be the same as your mu St. And this tangent P here will be the same as your mu SW. Okay, so it's up to you guys. I will give you option there. You can put it as R1 here with P, where R1 is the total of Ng and Fg. Okay, R2 is the total of NW and FW. Okay, or you can draw it just like this. I suggest to you to use this one because all the basics are here. Okay, for me, this one is much simpler because you know all the basics. This one is slightly more straightforward, but if you don't know about it, the way you do it, sometimes you can get lost. Okay? Any question here? Now, Deputy, did you get it? Good. Any question here? Apakah ada pertanyaan? Zakia? Are you here? I don't think that you are sure. Are you sure? Okay, good. Now, I think I have the next target for you. Okay, so this is the way to push it in. Okay, in order to get the P, the pushing force to push it in. Now, okay, now I want to draw the free body diagram in order to push it out, to pull it out. Okay. I want to draw the free body diagram to pull it out. Now, and I want to point out okay, later, your homework will consist of dry friction problem and this particular problem, picking problem and wedge problem. Okay, okay, you with the checkered shirt. Checkered shirt plus the pandemic hat. You have a pandemic hat. Your hair is quite long, right? It's pandemic hat. I call it a pandemic hat. Okay. Because you seem sleepy. Please help me to draw the free body diagram when I pull it out. I'm correct. To make you wake up a little bit. Right? Is it still for you? Yeah, okay, no problem. Don't worry, I'm not the one, the type of the lecturer who will angry with you when you are sleeping. It's not, no. This one is pushing it, right? But the one that I want you to do is if I pull the wedge in this particular problem out, instead of pushing it in, I want to pull the wedge out. And I want you to draw the pivot
Is
the wedge and the wedge of course as well. Because we will not be able to solve this particular pivot diagram without solving this. Okay? While waiting for your friend, okay, you seem sleepy as well. Are you sure? I don't think so. Don't worry, I can help you to stay awake. Are you sure? Yes. Why your face getting wet? Oh yeah, by the way, if I tease you a little bit, please don't get angry. Okay? This is the way I teach in the class. Why I teach like this? Because if I don't do that, most of you will get sleepy and just sleep in the class, right? But if I do this, you are forced yourself to stay awake, right? Right? That's the way I teach. That's why I don't like it when I have to teach online. Okay? When I call you and you don't respond back, I cannot do anything. Here, I can ask you to come. Okay? And in the next class, ask your friend to use the back second. So I can get more people to come forward. Don't use that. Use the basic one. The basic one. The basic one is the normal force and the body. And this one is actually wrong because the normal force is supposed to be perpendicular to the contact area. Right? Yeah, I will remind you again, okay? Your final exam will consist of all the things that you have learned from the game, okay? Until the things that you learned on Friday. Sorry, Thursday. Friday is unfortunately is already holiday. Not holiday, but I don't know what's the day for cuti bersama. Kan? It's actually not holiday, but it's cuti bersama. So if we come, I said, why not? Oh, we can still have the online class on it. You want it? No? Okay, why not? Okay, anyway, I will use it. So, Friday, okay, that one is Bu Anissa, is the coordinator of international class. So, if you have any problem with your study, you can complain to her. Okay. So the coordinator of international class there are two. Okay? The coordinator of mechanical engineering is Pak Ferianto, you know, right? The one looks slightly older than him, although he's younger than him. Correct? Why you are wondering, sir? Pak Ferry is the coordinator of mechanical engineering, and Bu Anissa is the coordinator for the aerospace. Who here belongs to the mechanical engineering? Aerospace? Oh, so the boundary will split then after the boundaries will split after the first year. The friction force, losing, yep. This one. This one is supposed to be action and reaction. So if this one is going to the left, that one is supposed to be going to the right. Okay, good. Actually, you are missing one thing. That's supposed to be bottled with this. You can just put R here. Okay. You are with it? Have you moved?
Yes.
See, you want to come forward? No? Are you sure? What's your name? Huh? Oh, sincerely. If you need to come forward, if you need to say wake up, you can just raise your hand. Sir, I need to come forward. Okay, any of you here, okay? Don't worry about it. I will give you some problem to solve it for. Okay, the other order. You need to come forward. Oh, you're that here? Why? No one of you likes to come forward. Why not? I will not make fun of you in front, right? Just ensure that you understand the problem and how to solve it, so you don't. I'm not like do I look like a kind of lecturer that will punish students who come forward? No, I won't. Okay. Just what's your name? Yeah, you. Dipa. This is what Dipa did. What do you think, guys? When we pull the wedge out, this is the free body diagram of the wedge. This is the free body diagram of the wedge. Is it correct? Try to think about it first. Okay? So, pulling force is going to the right. Friction force is going to the left. Here is the left as well, normal force. Normal to the contact. Okay? It's supposed to be the opposite of what we draw there. Okay? Then we have W, friction force, action and reaction always this and this. And normal here, action and reaction like this one. Okay. You are on the corner. Yes. What's your name again? Aurelia. Okay, Aurelia, what is it? You can't really see what the thing is correct. How can you determine that it's correct if you can't really see? Okay, anyway, you are there with the pandemic hat. Yes. What do you think? Is it correct or not? Are you sure? If you can't see, you can come forward. And I will give you some other problem. So, are you sure? Okay. Is it correct? Okay. Yeah, it is possible. Okay. This is collision where we have to pull the wedge out, and it's correct. It's the friction is supposed to be going to the opposite of the impending action. Okay, and there is a normal force here and here, and action and reaction, normal force, friction force, the way. Okay, and the way to solve it is just exactly the same. We solve first the first diagram, this one, the mass, the weight. Okay, in order to solve for R and W, because FW here is supposed to be NW multiplied by mu S W. Okay, we can solve for NW. Then after we solve for NW, then we can solve for NG and P. This one is NG multiplied by MSG. Okay, for mu S. Okay, any question about the wedge? When we push it in and when we pull it. Okay.
So the R up there is always opposite of the pulling side.
And not necessarily. It can be because we can see, right? There is a horizontal component of this one, NW. There is a horizontal component of NW. So it depends on the angle and it depends on the coefficient friction. It can be going to the left, it can be going to the right. But if you completely and the result is negative, means the direction is supposed to be opposite. So actually you can assume anything here. Okay? You don't have to worry about it. But remember, R is supposed to be the resultant of the contact here and here. Okay? Any question? The one on the top, sorry, the one on the left, but the one in front of it. Yep, you. Any question? Are you sure? You need me to wake you up? No. That's okay. If you need, just raise your hand and you come through, okay? If there is no question, then I will continue. Yeah? So this is it. To lower the load, just now, if friction force, oh yeah, because we have a friction force here, because we have a normal force, okay? Then we have P there, right? If we make a resultant of NG, FG, NW, FW, right? We can get it like this. Okay, we can get it like this. But okay, one thing there, yeah. If you take a look here, all the resultant here and here are slightly going to the left instead of to the right, right? So in that case, we have to pull it out in order to ensure that it can move up, right? Okay. And now, I want to talk about one more thing. There is a self-loathing here. When I talk about self-loathing, okay, self-loathing means after you push the wedge in, okay, the wedge will stay there. When you remove the force, after you push the wedge in, and you remove the force, the wedge will stay there. It means the wedge has a self-loathing mechanism. Ya, jadi setelah kalian dorong wedge-nya masuk, oke, si wedge itu akan diam di sana setelah gayanya dilakukan. Ya, kalau kondisinya seperti itu, artinya wedge-nya memiliki self-locking. Dia terkunci, mempunyai mekanisme penguncian di sana. Nah, untuk bisa memastikan bahwa suatu wedge itu punya self-locking atau tidak, itu batasannya itu. Ya, batasannya ini. Alfa lebih kecil daripada 2V. Ya, alfa lebih kecil daripada 2V. Itu batasannya. Alfa itu apa? Alfa itu adalah sudut dari si wedge. Ini. Oke, yang ini ya, ini alfa. Sudut dari si wedge. Sedangkan V itu apa? V itu adalah tangent V, ya. Tangent V itu adalah mu S ya. Tergantung dari surface bawah atau surface atas. Kalau mu S yang berapa? Surface bawah, tangent V-nya adalah mu S berapa? Sedangkan kalau surface atas, tangent V-nya itu adalah mu S dari si perbatasan antara massa dan wedge seperti itu. Nah, batas untuk self-loathing adalah alpha lebih kecil daripada 2 pi. Itu adalah batas untuk self-loathing. Kenapa seperti itu? Saya agree and you are also. What's your name? Diva. The one behind Diva. Huh? Edo. Okay. Seems like I need to wake you up a bit. Edo, what's the reason? Apa alasannya? Kenapa kok self-loathing itu terjadi apabila alpha di bawah 2 pi? Ingat, tangent V itu adalah sama dengan mu S-nya tergantung dari surface-nya ya. Seperti itu. Tadi saya sudah sempat tuliskan. Tangent V itu sama dengan mu S. Oke. Kenapa kok bisa seperti ini? Tangent V 2 kali T. Alpha itu harus lebih kecil daripada 2 kali P. Supaya terjadi self-loathing. Ini salah satu hal yang ketiga ya. Tadi saya bilang, when I talk about it, when I talk about the wedge, there are 3 important things. The first one is when you push the wedge in. The second one is when you pull the wedge out. Okay, the third one is the condition to ensure the self-loathing. Okay, if self-loathing is not happening, if alpha is bigger than 2 pi, the things that will happen is the wedge, after you push it, it will move out by itself. Jadi kalau misalkan kondisinya itu adalah alfanya lebih besar daripada 2 pi, ya, sudut dari wedge ini lebih besar daripada 2 pi, yang akan terjadi adalah wedge-nya setelah kalian dorong masuk gitu ya, kalian biarkan dia akan keluar sendiri. Itu bisa terjadi kalau sudut dari wedge-nya terlalu besar. Dan terlalu besar itu batasannya adalah 2 pi. Nah, yang ingin saya bahas sekarang, kenapa batasannya 2 pi? Perkirakan dari gambar si diagram benda bebas ini, ada yang bisa memberikan input tadi? Kenapa seperti itu? Kenapa kok bisa apabila alpha yang lebih besar daripada 2 pi, kemungkinan wedge-nya akan keluar sendiri? Ya.
The alpha is equal or more than 2 pi, and there's no buffer area.
What do you mean?
When the alpha is smaller than 2 pi, there's like a buffer area where the forces cancel each other. So if they into another force, so the weight will stay much more.
The idea is correct, but you haven't explained it completely yet why it moves.
Because there's 2 pi of the end. So like jam pasir.
Tempatnya. Oke, idenya mirip ya. Bentar. Intinya adalah, jika kita punya alfanya itu lebih besar daripada 2 pi ya. Nah, ini bisa dicoret-coret di sini. Nah, kalau alfanya lebih besar daripada 2 pi, itu artinya sudutnya cukup besar gitu ya. Ini misalkan alfanya itu misalkan sama dengan 2 pi, nanti yang akan kalian dapatkan ya, dia itu tidak akan keluar kalau kondisi yang lebih bawah itu tidak akan keluar karena resultannya itu akan cenderungnya miring ke kiri. Jadi kan pergerakan keluarnya itu kan cenderungnya ke kanan ya. Pergerakan keluarnya itu cenderungnya ke kanan. Oke. Pergerakan keluarnya itu cenderungnya ke kanan. Nah, kalau misalkan ini kita punya alpha, V ya, ini kita punya V, lalu ini V yang bawah, lalu di atas juga misalkan friction coefficient-nya itu sama dengan asumsi friction coefficient-nya sama. Ini adalah normalnya ya. Oke. Gambarnya kurang pas. Oke, itu adalah normalnya ini. Ya. Sorry, normalnya tidak seperti itu. Ini kondisi batasnya. Ini normalnya misalkan seperti itu ya. Nah, kalau misalkan apa namanya? Oke, sorry. Ya, sorry sedikit ya. Ini adalah normalnya, jadi gaya normalnya itu ke sini. Ini adalah permukaan normalnya ini ya. Kita biar gampang kelihatannya ini masih jadi bingung kali. Warnanya saya bedakan. Ini adalah permukaan normalnya. Permukaan normalnya yang sangat-sangat miring. Oke, itu adalah permukaan normal. Nah, kemudian ini ada lagi resultan yang sisi atas. Resultan yang sisi atas itu adalah normal ditambahkan dengan gaya gesek ya. Dan itu akan jadi seperti ini. Salah lagi. Kan jadi seperti ini. Ini adalah R1, ini adalah R2. Normalnya, permukaan normal tegak lurus yaitu yang saya birukan. Itu adalah permukaan tegak lurus antara si surface dengan massa ya, wedge dengan yang massa yang atas. Oke, kelihatannya permukaannya kurang miring ya. Saya berikan. Nah, ini adalah kondisi batas self-loathing. Yang biru, ya, yang biru ini adalah normal tegak lurus terhadap si permukaan atas. Oke, kemudian R2, R2 itu adalah resultan antara gaya normal dan gaya gesek dari permukaan atas. R1 adalah resultan dari gaya normal dan gaya gesek dari permukaan bawah. Bayangkan ya? Ini V, yang atas juga V. Kita anggap kasusnya adalah coefficient of friction di sisi atas bawah sama persis. Ini juga V sudutnya. Oke, mu S G dan juga mu S W itu sama persis. Nah, kalau kondisinya seperti itu, ini ada V, ada R1 yang cenderung ke kiri. Ini ada R2 yang sebenarnya cenderung juga ke kiri. Kalau kita lihat terhadap permukaan normal, cenderungnya ke kiri ya. Itu kalau permukaan normalnya. Itu kalau kita bagi R2 itu, nanti normal force-nya arahnya ke bawah, gaya geseknya sebenarnya arahnya ke kiri. Tetapi kalau kita jumlahkan R1-nya, secara total masih ada agak arah ke kanan karena normal force-nya itu sangat-sangat ke kanan. Kebayang nggak? Rafi, can you imagine? Ini permukaan normalnya. Normal force sesuai dengan permukaan normal kan? Sesuai dengan apa? Tegak lurusnya. Itu arahnya ke kanan banget. Karena sudutnya besar kan di sini alfa ya. Gaya geseknya arahnya masih ke kiri. Tetapi setelah ditotalkan, resultannya itu masih agak ke kanan. Karena permukaannya sangat-sangat miring, kebayang ya? Ini kondisi batas self-loathing. Nah, kondisi batas self-loathing itu terjadi saat R2 dan R1 itu segaris. Bisa lihat ya, itu segaris kan? Makanya tadi itu saya bingung gambarnya karena harus segaris. Sudut alfanya besar sekali. Sudut alfa ini itu terlalu besar. Batas alfanya untuk self-loathing itu adalah 2 pi. Itu adalah batas maksimumnya, harusnya lebih kecil daripada itu. Nah, ini adalah kondisi ya, yang ada di sini. Ini adalah kondisi ekstrimnya. Batas antara self-loathing terjadi dan self-loathing tidak terjadi. Resultannya ada di geseknya ke kiri, tetapi resultannya masih ke kanan. Dan resultan 2 itu segaris dengan resultan 1. Ya, segaris dengan resultan 1. Itu adalah kondisi ekstrim. Nah, kalau kalian lihat di situ, yang sisi atas itu sudutnya V, yang sisi bawah sudutnya V kan? Betul kan? Dan 2 V tersebut kalau dijumlahkan hasilnya akan sama dengan alfa. Kebayang? Makanya ini jadi kondisi ekstrim kita. Karena kondisi ekstrimnya diagram bebasnya seperti ini. Itu penjelasannya. Apakah bisa ditangkap? Ini adalah batas self-loathing. Paling ekstrimnya adalah yang masih bisa self-loathing itu sedikit, alfanya sedikit di bawah ini. Ini batas ekstrim. Saat gaya R1 dan R2 itu benar-benar lurus. Oke? Tidak ada pulling force, tidak ada pushing force. Hanya ada total normal force dan friction force dari bawah, total normal force dan friction force dari atas. Dan itu dia membuat garis lurus. Itu adalah kondisi ekstrimnya. Dan kondisi ekstrim ini terjadi saat alfa sama dengan 2. Audrey, apakah dipahami? Ya, Audrey. Oke, you. Ya. Dipahami kan? You. In front of you. The sleepy one just now. Yeah. I asked you just now. You understand? Huh? Okay, then try to discuss it with your friend. What's your question? Yeah. Impending motion, that's condition of impending motion, without any pulling force and pushing force. Without any pulling force and pushing force. So, that's the limit. In order to ensure that self-loathing, we have to ensure that alpha is less than 2. Okay, do you get it? So later, if you are asked, what is alpha to ensure the self-loathing? This is it. Where V is tangent, tangent mu s. Okay, sorry, tangent alpha P, tangent V is equal to mu s. Okay, now my question. If mu s of the top one and the bottom one is different, what is the limit of self-loathing? Anyone can answer. If mu s of the top wedge friction and the bottom wedge, if the mu s of the top and the bottom wedge are different, okay? What is the value of alpha? Please not the hard, if you understand. What do you think, sir?
It just add all of the
Yes, correct. Just add all of them. So P of the bottom one plus P of the top one, that's the answer. Okay? This is only happening if the friction force are the same. Sorry, the mu s is the same for the top and bottom. If the mu s is different, then alpha will be the same. The limit is P1 plus P2, where P1 is the bottom one, P2 is the top one. Okay, tangent P1 is equal to mu sg, tangent P2 is equal to mu s double, something. Okay, you get it, guys? Okay, it's already 30 past 8. Don't forget that after this you need to check the homework, okay? Some of the homework will be there about the wedge as well, okay? These are the homework that I will give to you guys, right? It's wedge, wedge, wedge. This is one of the problems. And maybe number one will be this one from the previous example. Okay, so we will have 5 homework problems. Why 5? Because that will be your last one. Unless you want additional one just before that. To help you to study on the holiday. You want homework on the holiday? No? Okay. In that case, I will give you 5 problems for the next homework, for the last one. So the last homework will be, you will need to submit the last homework on Thursday, next week. Okay? And there will be 5 problems. Online. Okay? Because the one that will grade will be my answer. I will grade your exam, but the homework will be graded. Okay? I think that's all for today. Thank you very much for coming. Okay. See you again next week on Thursday at 10 in the morning. Okay. See you guys. Bye.